All right, let's dive in. We're going to talk about something that I know can feel a little intense, physics formulas. But here's the thing. I want you to forget about them as scary equations you have to memorize. Think of them as the actual language the universe is written in. I mean, have you ever felt like you're playing a game but you never got the rule book? Well, that's kind of what being alive is like. And it turns out there is a rule book. Physics is basically the study of those rules. And the formulas, that's just how we read them. They explain literally everything, from an apple falling off a tree to a galaxy spinning in space. And that is the big secret. Once you get what they're saying, they stop being these annoying roadblocks. They become something way cooler. They're like cheat codes. Yeah, cheat codes that let you actually understand and even predict how everything around you is going to work. Okay, so where do we even begin? Let's start with the absolute foundation of physics, motion. I mean, before we can get into the why stuff moves, we first got to get a handle on the language for describing how it moves. It seems so basic, doesn't it? How fast is something going? You're driving, you glance down at the speedometer, but what is that number really telling you? It's not just a number. It's telling you about a relationship, a connection between things, and it's described by a beautifully simple formula. And here it is, our very first cheat code, and it is an absolute classic. Speed equals distance divided by time. That's it. That's the whole rule. It's just how much ground you cover in a certain amount of time. Now, for this to work for everyone, everywhere, from a lab in Japan to one in California, scientists need a shared language, right? So they agreed on standard units. For them, distance is always in meters and time is in seconds. That's why in science, you'll almost always see speed measured in meters per second, not miles per hour. And you might be thinking, okay, great for my physics homework, but it's so much bigger than that. This one simple idea is the foundation for everything, from planning your commute to navigating a plane to figuring out how fast planets are zipping through space. It's everywhere. Okay, let's level up. We've got the language to describe motion now. But what actually causes it? I mean, what makes something speed up, or slow down, or turn a corner? The answer to all of that comes down to one single powerful idea: force. Think about it. Anytime anything accelerates, a soccer ball getting kicked, a car hitting the gas, even a satellite staying in orbit around the Earth, there's a force making it happen. Force is the why that explains the how of all motion. And this is probably one of the most famous and important rules in the entire physics playbook. You've probably heard of it. F equals ma. Force equals mass times acceleration. It's so elegant, right? If you want to make something accelerate faster, you need more force. And if the thing you're pushing is heavier, more massive, well, you're going to need more force for that too. Makes perfect sense. So, back to our standard units. Mass is measured in kilograms. Acceleration, that's in meters per second squared. So technically, the unit for force is a kilogram meter per second squared. Yeah, try saying that 3 times fast. It's a total mouthful. So scientists did us all a favor, and in a tribute to the man himself, they just named the unit of force the Newton. Much better. And what's so cool is how versatile this idea of force is. Look at this. F equals ma, that's the general rule, right? Like pushing a box. But then you've got gravity. The force of gravity on you is your weight, and we figure that out by multiplying your mass by g, which is just the special acceleration caused by gravity. Or look at a spring. The force there depends on k, which is just how stiff the spring is, and x, how much you stretch it. See? They're all just different flavors of the same core idea, force. And this is why engineering is basically applied physics. If you want to build a bridge that won't collapse in the wind, or design a car that can stop on a dime, or launch a rocket powerful enough to escape Earth's pull, you have to be a master of understanding and calculating forces. It's absolutely crucial. Okay, so let's recap. We have motion, and we have the force that causes motion. So the next logical question is, what happens when a force actually does its job and moves something? Well, that's when we get into 2 new, totally linked concepts: work and energy. Now, in everyday life, Work can mean anything, but in physics, it's super specific. Work is only done when a force you apply actually moves an object over a distance. So get this, if you push against a solid brick wall with all your might for an hour, you're sweating, you're exhausted. In physics terms, you've done zero work because the wall didn't move. Kind of brutal, right? And the unit we use to measure this work is called the joule. But here's the really important part. Where does that work go? It doesn't just vanish into thin air. The work you do on an object gets transferred into it, and it becomes energy. And that energy basically shows up in two main flavors. On one side, you've got potential energy. Think of it as stored energy, or energy of position. The formula tells you it's all about mass, gravity, and height. It's the roller coaster car sitting at the very top of the highest hill, just waiting. It's packed with potential. Then on the other side, you've got kinetic energy. That's the energy of motion. Its formula is all about mass and speed. So that's a roller coaster as it's hurtling down the track. And what's happening? It's trading that potential energy from its height for kinetic energy, for pure speed. Okay, we've gone through the cheat codes for motion, for force, for energy. But now we've come to the final and maybe the most important part. This is the master key. This is the one thing that will take you from someone who just memorizes formulas for a test to someone who actually speaks the language of physics.
See, the real power isn't just knowing the formulas themselves. For example, knowing that speed equals distance over time is great. But what happens if you already know how fast you're going and for how long? And what you really need to figure out is the distance.
Well, here's the thing. It's knowing that you can flip these formulas around to find any missing piece of the puzzle. An equation isn't a rigid one-way street. It's a description of a relationship. And with just a tiny bit of algebra, you can rearrange it to find whatever you're looking for. Look, let's go back to our very first formula. The standard way is speed equals distance over time. Perfect if you need to find speed. But what if you're on a road trip and you know your average speed and how long you've been driving? You just flip it around. Distance equals speed times time. Or what if you need to know how long a trip will take? Easy. Time equals speed divided by distance. It's like getting 3 tools for the price of 1, just by understanding one single relationship.
And this isn't just for speed. This master key works on every single formula we talked about today. You can rearrange F equals ma to solve for mass or for acceleration. You can flip the energy formulas around to find out how high something was or how fast it was going. You see, you don't need to memorize dozens of different equations. You just need to understand the core relationship. That's where the real power is.
So from now on, try not to see these as just problems on a page. See them as a new lens for looking at the world. The next time you see a bird take flight, or a car slam on its brakes, or even just drop your keys, you'll know the secret language that's describing exactly what's happening, the beautiful physics behind it all. So now you have the keys to the language of the universe. The only question is, what will you unlock?